now that we've talked about creativity and some methods to enhance the creative thought process, I want to specifically look at how this can be applied to technology projects. So before you've gotten to this step, you have to remember that you've searched externally, you've conducted some literature searches, you've reviewed patents, you've benchmarked ideas, and you've interviewed some experts. So you're already kind of familiar with the solutions that are out there. And so what we need to do now is to develop some concepts for our projects that aren't limited by the research that we've done, but instead are enhanced by the research that we've done. So we need to avoid the cliche that we just try to reinvent the wheel. It's difficult because part of the research project process is that we see what solutions have always been presented, and as we know now that there's a creative bias to try to solve solutions in a similar manner. But so now we need to apply some structured processes in concept generation related to technology projects. So the first is brainstorming sessions, and in a brainstorming session, the team members get together to generate many concepts in a very short period of time. This really should be an unstructured activity that involves the 5 basic rules listed here of no evaluation or judgment of ideas. You really should encourage wild ideas. You really want to focus on quantity over quality. That usually is difficult for engineers to swallow. You can toss bad ideas out later, but right now you want a lot of them. You want to build upon, combine, or modify ideas of other people in the group. So there should be a dynamic happening. Somebody comes up with an idea that sparks an idea in somebody else that they build upon. Maybe 2 people have separate ideas, but they're somewhat related, so you combine them together. In this process, you can use a lot of those scamper principles that we went over in the previous video. And then finally, you want to make sure that you record all these ideas. You want to have a record of the brainstorming process. Sometimes brainstorming, especially with engineers, results in everyone sitting around staring at each other, twiddling their thumbs. So there's a little more structured process called brain writing, which I suggest if you feel uncomfortable with the brainstorming process. And in brain writing, the team starts with a problem statement, and then each team member writes an idea down on a card. So instead of being oral, it's written. And so you write this idea down on a card and you place it in the center of the table. So you take 5 minutes, you fill out, let's say, a 3x5 index card. All of those get then collected in the center of the table. And these are the idea cards that I'm listing in that bulleted point list there. Once the ideas are collected, another team member is going to take a card from the pile and use that idea to generate a new idea. So it kind of slows the brainstorming process down. It makes it written instead of oral. Those techniques can tend to help move the process along. Another much more structured brainstorming-like technique is the process of nominal group technique, or NGT. And in this process, the problem statement that you're trying to solve is read aloud by the team member. Each team member is then going to restate the problem in his or her own words to ensure that all members understand it. This is a really important point in that it really helps to clarify that everybody has the same understanding of what the problem is that was generated in the problem identification stage. After everyone has had a chance to restate the problem in his or her own words, you're going to sit and take some time and silently generate some ideas on a piece of paper. So it's kind of like individual brainstorming at this point. You then use a round robin technique. You're going to present one idea in a turn until all of your ideas are exhausted. So somebody's going to go around the table and start and present their first idea. The next person presents the next idea, etc. A facilitator, as this is happening, is going to clarify the ideas as they're stated by the individuals of the team, and then write them in a location where the entire team can view them on a whiteboard, on a large piece of paper, something to that effect. Once every member has expressed the ideas that they generated during the individual brainstorming session, the facilitator is going to lead a discussion to clarify and rephrase any of the ideas. You also then want to collect like ideas together. You know, people may have delivered ideas that are similar with some small nuance that are obviously related to one another. Alternatively, people could have generated ideas that are very divergent in their approach to the problem. So you want to group like ideas together. Then once you've got a big collection of ideas, each person in the group is going to cast 3 to 6 votes for the ideas presented. So everyone gets an assigned number of votes, equal number of votes. Typically this is more than one. 3 to 6 is common, and you vote for which ideas you like the most. You could give 1 vote per idea. You could give multiple votes to a single idea if you believe strongly in it, such like that. The outcome is then set or prioritized ideas that the team can further discuss or peruse. So you've got these ranked ideas via group input. Concepts could also be systematically generated using a technique called a concept table, which decomposes a problem into subfunctions and solutions related to those different subfunctions. So here I'm showing a table that's been constructed with headings that identify the functions that need to be achieved in a design. So in this design we need a user interface, we need a display, we need connectivity and expansion capability, there has to be electrical power, and there has to be some size requirements or size functions. The entries in the columns represent potential solutions to each of those functions. So we'll just look at user interface. Here, for example, there's 5 different user interfaces, ways that the user can interface with this device. They could use a traditional keyboard. The keyboard could be replaced with a similar device, but that is a touchpad. Maybe you want to use handwriting recognition instead of a keyboard or touchpad. Perhaps the device videos the user and is able to interact with the user through face recognition. Alternatively, maybe the device is voice activated. So those are different solutions to the user interface. So novel products or solutions can then be generated by combining elements from each of the columns, and you can use one element from a column or using multiple elements from each column. So we could easily envision a device that uses handwriting recognition and voice interface via an LCD over USB wireless internet and is solar powered and wearable. You know, you can select different cells from each of the columns and combine those in new and unique ways to generate some concepts. Another tool is a concept fan. Here is a graphical representation of design decisions and choices that need to be made. In a concept fan, decisions are identified by circles, and solutions to those decisions are identified by squares. So in this example, we're showing a concept fan for that temperature measurement and display device from several lectures ago. So we've got the overall design. We have to have a display to the user. We need to make a decision about how that display is going to be structured. We need to convert temperature to voltage, and we have to make decisions on different ways that can be approached. We could use a transistor or an op-amp. If we use a transistor, there are several different alternatives. If we use an op-amp, there are several different alternatives. And then there's some similar design decisions that need to be made about the temperature sensor itself. So, and again, just like the previous example of a concept table, a concept fan, you can create unique solutions by just combining different levels of the solutions here, indicated again in the squares. So similar to the table, but maybe it appeals to a more visual design decision process. So that ends concept generation. The next process, after techniques like brainstorming have been used to generate ideas, is to evaluate the ideas. They need to be evaluated to determine which are the most promising to pursue. Which one of the ideas, or which of the ideas in the previous process, are we going to continue to work on? Obviously, we need to down select those ideas. So this process is to take user needs, concepts, and engineering considerations, take all that input data and apply some sort of engineering process that ranks the concepts. We have to have a decision-making process at play here. And we're going to introduce a few different decision-making processes. Some of the most popular techniques are a strength and weakness analysis, a decision matrix, or a PUE Concept Selection method. So I'm presenting here a strengths and weakness analysis of a proposed method for heating an Intel chip to perform life cycle testing. So the idea is we need to heat the chip up to accelerate its aging process. And the method presented in the strength of weakness analysis is that we list the different proposals. In this case, we have two: contact heating, where we put a heater directly in contact with the chip, or temperature chamber, where we put the entire chip inside of a temperature. And we just list the strengths and the weaknesses of each approach. So one strength for contact heating is that it's a simple design. You just put a heater in contact with the chip. The weakness is that it's harder to control. A temperature chamber, in contrast, has a strength that it performs a uniform temperature. However, it's a much more difficult to design controller. So you would list all the strengths that you can think of for each method and then all of the weaknesses. So this method is simple. The different solutions are listed. Bulleted lists of strengths and weaknesses are presented. It's a very quick way to compare ideas, but it has a major limitation in that it does not require uniform criteria for comparison. So it's pretty hard to compare simple design versus no uniform temperature, for example. So it's not a one-to-one and apples-to-apples comparison. It also doesn't provide quantitative evaluation of ideas. How much more important is simple design than uniform temperature capability? What's the trade-off between those two strengths and weaknesses? And this technique of strengths and weakness tables doesn't really address that. That being said, it is a good first order down select. If you got a lot of competing ideas and you just need to list their qualities for an initial down select, this procedure can be used for that purpose pretty well. Really what you should be getting to, though, are more quantitative ways to evaluate designs, and one of the most popular is the analytical hierarchy process. It's a 5-step process. The first is to determine the selection criteria for the different design options. Then we need to assign each of those criteria a weighting factor. We then need to identify and rate alternatives relative to the criteria that we've identified. We then compute the scores for each of the designs based on how they fit that criteria, and then we need to review the decision. And I'm going to demonstrate this technique with an example. It's similar to techniques that we've seen in other stages of the design process. So here we have 3 different concepts for the design of an electronic circuit for measuring temperature by producing a voltage signal that is linear with changes in temperature. So step 1 is to determine the criteria on which the designs are going to be evaluated. So step 1, select the criteria. And here we have 4 criteria that we've decided on: accuracy, low cost, small size, and availability of parts for manufacture. Most likely the criteria for these designs are related to the problem statement and problem requirement steps that we've already previously identified in the engineering design process. So this list probably will come to you pretty easily because you've already done most of this work when you get to this point in the design process. Next, we need to determine the normalized weighting factors. So this is done as was done in a previous lecture. So, this is the same weighting factor table. You'll see that the columns here and the rows here have the same titles, and we've used this relative weighting. Accuracy compared to accuracy is a 1. Accuracy should be 5 times as important as cost, etc., etc. And then we use that normalization method that we discussed previously to assign an overall weight to each of the evaluation criteria. So exact same mathematical process as we've applied in the past. Step 3 is to compute the design ratings. So design ratings need to reflect the technical merit of each of the design options relative to the criteria stated in the previous step. So in this step, you somehow need to give each design option a score in which a higher rating reflects a better match to the criteria that you've identified. And for each of those criteria, you're going to need to use your judgment on how to do this. So there's not one size fits all kind of approach here. So I'm going to give one example. So in the case of the temperature monitoring device, accuracy is one of the criteria that we identified in the previous step. And so how are we going to identify accuracy of the circuit? Well, what we decided to do here was evaluate the circuits according to a SPICE analysis with 10% resistors. So what we did is we measured the deviation in the output voltage, meaning that we measured the change from the nominal voltage from the 3 different designs. And what we discovered was that for the first design, there's a 9.2% deviation. For the second design, there's a 1.3% deviation. And for the third design, there's a 1.9% deviation. And our goal here is we don't want a lot of deviation. We want to minimize the deviation. The less deviation, the more accurate. So we take the minimum of the 3 deviations here, and then we divide by the deviation of each circuit. So the result then assigns a score of 1 to the lowest deviation option. So you see the minimum deviation of these 3 circuits, as was determined via a simulation of the output voltage, was 1.3. So this circuit, circuit 2, was the most accurate, and so therefore it gets a rating of 1. So circuit 2, relative to criteria 1, got a rating of 1. Circuit 1, related to criteria 1, was much less accurate. It was only it had 9.2% deviation, so it gets a rating of 0.14. And then circuit 3, related to criteria 1, had a deviation of 1.9, so it gets a rating of 0.68. So we can see that the higher the number, the more accurate the method, and additionally, they're ranked against one another. So we clearly see that design option 2 is the most superior. However, design option 3 has a relatively high level of accuracy. Both of them are much better than design option 1, all related to criteria 1, which was accuracy. The process would then have to be repeated for each of the different design criteria. So for this particular example, there's 3 designs and there's 4 criteria, so you would have to come up with 12 scores in total for computing your design ratings. Finally, after each of the design and criteria combo has been ranked using an appropriate method, you need to build yourself a decision matrix, and you need to calculate an overall weighted score for the different alternatives. So we've got the weights that we evaluated for each. This block would get the different scores. These blocks, would get the different scores for each of the criteria, and then you would multiply the score for each by the weighting factor, and then sum them to get a total score for each of the devices. So then that allows you to review. Step 5 was review, so you would review the scores. This is still a relatively subjective process, particularly based on what metric you use to rank the different designs according to the different criteria. Sometimes they're very objective, sometimes they're very subjective. You just have to be comfortable with that. That being said, the highest score doesn't necessarily mean the best design. It just it allows you to do a little bit more apples to apples comparison between the designs. There may still be reasons you don't want to select a specific design, and this process may actually show you that you need to go back and develop some different requirements to maybe better differentiate the different designs if that's the case. There is a similar technique, but a little simpler, that I actually prefer. It's called PUE Concept Selection, and the reason I prefer it is because it doesn't give you a numeric output. It just is a better or worse but it does have a little bit of weight associated with it. It's got a simpler scoring procedure. It's also iterative, which I like. So the process has 8 steps. First, you select the comparison criteria. You then determine the weights for the criteria, determine your different concepts that you're going to evaluate. The next is a little different than what we've done before. We need to select a baseline concept. It's just your perception of which of your different concepts you believe to be the best. You then are going to compare the other criteria or the other concepts to the baseline in each of the criteria areas. You're going to give it one of 3 ratings only. Is this better than the baseline? Is this equal to the baseline? Or is this worse than the baseline? And better to gets a score of +1, equal to gets a 0, -1 gets a worse than. Then what you do is you multiply those scores by the weight for each of the criteria. You then examine the total score and you retain, update, or drop. So what you want to do is you want to look at what looked better, what looked the same, what looked worse. Can you eliminate some features? Do you need to add some features? Do you need to combine some features? In essence, how do we synthesize what we know to be better, what we know to be worse, etc. It's not always possible, but that's the goal there. Then what you do is you go back and you are at the determined concept stage again, 3, right? After you've synthesized, in essence, you've got new concepts. So you repeat the process and you update your tables and iterate, and eventually this process is going to result in a best concept. Good practice is that you have to iterate, so you should go through the PUE Concept Selection process at least a minimum of 2 times, right? You should go through with your initial ideas that you generated from your brainstorming or your brainwriting activities or whatever you used in the concept generation stage, and then you need to, in essence, refine them using this PUE selection method. So here's an example of a table that is used in the PUE concept selection method. We've got option 1. You use that as your reference. You've got different criteria, each with the weighting. And then what you do is you compare each of the design options to the base case. Again, you get a score of 0 for same, you get a score of +1 for better, you get a score of -1 for worse. Then what you do is you just multiply this score by this score by this score by this score by this, and then sum them all. So we see that option 2 gets a +4, so it looks like that's a good option to retain. Option 3 got a -4 compared to the reference case, so we would eliminate this. Option 4, it got a +5, so we also want to retain that. So do we want to continue? We've got some different options. It looks here that option 2 is different enough from option 1 that it can't really be synthesized into it, so we want to retain it though. Option 4, it looks like it's got some features that we might be able to combine with the base case, so our recommendation there is to combine those. So in the next iteration, we would only have 2. We would have the base case and then option 2, where the base case is the combination of option 1 and option 4. So we would want to do that a minimum of 2 times, that iteration process. So that leads us to final project gate 6, which is the concept generation gate. And so I won't bore you with reading through this, and you can read it all on your own. This has been posted to Blackboard, and the instructions for the submission is posted there too. Big picture, what you need to do is you need to do a brainwriting and a PUE concept selection step. So that's FP6. Thanks again for your